Welcome to the course. We're going to be learning applied statistics using R for biological sciences. And the first thing you really need to do in this course is you need to download R for your computer. R is free software. It's super powerful statistical software. You can go to the website r-project.org. You can download R, and you will want to basically scroll down on the web page to find United States. Really, the only difference is the speed at which it'll download, but if you go to someplace in the USA that's close to where you are, well, if you're not in the USA, go to wherever in the world is closest to you, download it and install it. After you install R, you'll want to install Rstudio, which is kind of an upper layer on R that is makes it much easier to use. And this is at rstudio.com, and it's free also. There's a download link at the top of the page, and when you want to download Rstudio Desktop and the open source license, it's got everything you need. And it's free, and it's available for whatever operating system you're using. Once you have RStudio, this is kind of what it'll look like. Now I have some stuff open. This is more or less what things will look like. I already have. So I have R is a console-based software, which means that you'll have a console prompt that's waiting for input. It looks like this little greater than sign, and it's going to be waiting for you to input something. R is built around the idea of expressions and objects. So an expression is like what you want to do, and an object is the things you want to do that thing to. And so this is a very general definition, I admit, but we'll be learning about the different kinds of expressions and the different types of objects as we learn. And then we'll also be learning some statistics stuff that goes along with all of this. So the first thing that you should be aware of for R is you can kind of use it as a calculator. So as input, you can input something like 8 plus 9. If you hit enter, you'll get the answer 17. It's going to give you this output in this format where you see the little 1 in the bracket. What that means is your output has it's a list of your output is going to be a list of numbers. This number list only has one thing in it, but it's indexing it. So the first item in your output is just indexed with number 1 because the first thing in your list, but it's the only thing. Later on, you'll be having more things in your output, and so the index is going to mean something then. Right now, that 1 is going to be there every time. So other subtractions, 6 minus 12, I get negative 6. Type in something like 9 times 3, 27. Let's do division. 7 divided by, let's say 7 divided by 13. I get 0.5384615. It's rounding off to the nearest 7 decimal place, but you can change that. We'll talk about how you could change it later on. So to do exponents, to do powers, you use the caret, which is over the 6 button. So, for example, if I wanted to take 6 to the power 3, that would be 6 to the third, right? So we're going to get 216 for my answer. Okay, that's how you do exponents. You can also do fractional exponents. For example, let's do 2 to the no. I don't have to put a space between my caret, but I have been doing that. To the 0.5, that's if you're savvy with your math, that's a square root, and I'm getting 1.41. Maybe it's not so obvious that's a square root. Let's do 4 to the power 0.5. You get 2 for your answer. But you can also do that in different ways. You could say 4 to the power of 1/2. You could do it like that. You can put the 1/2 in parentheses. So R uses parentheses for the order of operations. If I wanted to make 1 divide by 2 first and then take 4 to that power. For square roots, though, there's another function call you can use, Sqrt. So Sqrt4 is the square root of 4. And this is the first function that we're looking at here. It's so the function is the Sqrt function, the square root function, and it takes an input of 4, and that's why we need those parentheses there. And that's very common. That's a syntax that we'll be using a lot, functions. And now this might be the first function you've seen, but you'll be seeing other functions. Some other stuff. Pi is a constant that's saved in R. So pi. If you do capital Pi, it's going to not know what I'm doing. R is case sensitive, so if you don't put things in the right case, it's going to be upset with you. Let's see. If you wanted to do an exponential, the constant e, you would think that just putting in the letter e would get it for you, but that's not the way it works. Not the way pi, not like pi. You'd have to do exp and then you'd put 1. The exponential to the power 1. That's e to the power 1. That's going to give us 2.718282. This is the constant e. If you remember from logarithms, that's important. In fact, if you do a logarithm you can do a logarithm using the log function, the logarithm of 8. What that is giving you is the power to which, so if I take exp 2.079442, this should give me roughly 8. Yeah, it's giving roughly 8. So the logarithm of 8, this is a natural logarithm. If I wanted to do a logarithm with base 10, there's a different function for that. It's log 10. Log 10 of 1,000, what power do you raise 10 to get you 1,000? 10 to the third gives you 1,000. That's what log 10 will do. And there's also log 2, which is useful for comp sci stuff. That's a base 2. So 2, but you can actually do log with any base. You can just specify the base. So the logarithm of 1,000 base equals 37. You can specify the base in this way, and this is telling me that 37 to the power 1.913019 is going to be approximately 1,000. Of course, it's rounded off by, the decimal places are rounded off, so it's not exact, but it's close. So anyway, I'm just showing you some of the functions you can do. You got the sine function, the sine of now the sine function is going to, if I put in the sine of 90, it's not going to like that because it's not working in degrees, it's working in radians. So I would have to put the sine of pi over 2, which is 90 degrees. That's going to give me 1, which if you're up on your trig, you would be expecting that. Anyway, I don't think we'll be using trig functions much. Just you can look it up and you can find any of those trig functions. Any of the, so you can do a whole lot of mathematical operations. But this is also the first kind of exposure to functions that we have. And so just generally, a function in R is going to look like, I'm going to put it a little number sign, function name, and then you'll have input 1, input 2, input 3, etc. Now in R, if you ever start your line with a number sign, it won't evaluate that code. It will just treat that as a comment. If you've had some experience with computer programming, it's very important to put comments in your code. that's ignored by the computer. That was a comment that is nothing is evaluated there. You could actually put a comment at the end of your code, something like sine pi over 2. I think this will be equal to 1, and sure enough it is. So when you put a number sign, the R will ignore everything after that number sign, and that can be handy if you want to kind of say something about what you're writing. But anyway, a function is going to be just the function name and then parentheses, and in the parentheses there'll be all of the kind of inputs that you want for that function. If you're not sure about a function, like let's say I'm not sure about the log function, type question mark and then the name of the function, question mark log, and just hit enter. And you'll see that you'll have on the right, you'll have a lot of information about this pops up under help. And it tells you that log computes logarithms by default, natural logarithms. You can use log 10, log 2, and others, log x comma base. So when you use what it gives here is log, when it says log parenthesis x comma base, the first thing it's looking for is the number it wants to take the logarithm of, and the second number it looks for is the base. So if I specify log x equals, let's do what we did before, 1000 comma base equals 37, it will give me the same answer I got before. In fact, if I just said log 1000 comma 37, it will be the exact same thing, because it assumes the first number I put in there is the number I want to take a logarithm of, and the second number I put in is the base. So if I put 37 first, as you can imagine, it's going to give me something wacky, right? But you can put, as long as you label them in your input, I can say base equals 37 comma x equals 1000. And if I do that, R doesn't care what order I put them in. So if I explicitly label my input values, you can do it in any order. But if you are not labeling them, it has to be in the order that R is expecting them in. So let's see. There's a whole lot of functions that are built into what's called base R. Base R is like when you downloaded R, that's what came with it. But there are also lots of libraries of functions that other people out there have created, and those are really useful. But you have to install the library first. So to install a library, they're actually called library packages. You can go under, so if you're in Rstudio, which I hope you are, if you go up to the menu at the top, you'll see Tools. You can install packages. And when you install packages, it will get a list of all the packages that are out there, and you want to install one of them. Let's see. I'm just going to type in the letter H and see what there is under H. HAC. I don't know what it is, but let's say I want to install it. I just selected it from that list, and I'm going to click Install. Now, what actually is the command you can see that was executed was, okay, looking at it now, it's install.packages and then in quotes HAC. It has to be exact. And then it goes through and it tries to do all this stuff automatically. If there's any problems, it'll fix it. And in the end, it'll say it's good. Now, I can't use this library right away. I need to kind of turn the library on. So I don't have to download it ever again, but I do have to, I have to type library HAC, and once I do that, oh, did I, maybe I have to put it in quotes. Let's try. Oh, it didn't, did it not work? Error. Oh, the library didn't install correctly. I should have done something that I knew about. Let's try one that works. Let's install packages. Let's do let's Earth. I'll bet you that's going to work. I'm going to install the package called Earth. It probably has a whole bunch of functions related to geographical or geological analysis of stuff. But you can see when I try to install this, it's going through a whole lot of necessary pieces. So now let's turn on library parentheses Earth, and it's loading all of the required packages, and now it's done. So any of the functions that are part of the Earth package are now available to me. All right. Now, one thing that I've as we put something in quotes a second ago, it's worth mentioning that when you R only understands straightforward double quotes, which are found, doing shift quote. These are just straight up and down. If you're working in Word and try to paste some quotes into R, it will be very upset with you. So I'll give you a little example. Now I'm going to jump a little ahead. I'll say test string. Now you don't know what I'm doing yet, but I'm going to say good. Now if I use the double quotes by doing shift quote, that's fine, but other test string, what I'm going to do is paste in something from Word. So here we have another quote. I'm going to copy this from Word and I'm going to paste it here. You notice that the quotation marks are now like an open quote and a close quote. I'm going to hit enter and I'm expecting R to yell at me. Yes, it doesn't know what to do with those things. They need to be the boring old double quotes that you get by pressing the quote button on the keyboard in R. In Word, it makes them fancier by turning them to open quotes and close quotes. So I want you to be careful of that, because if you're ever copying something in from Word into R, be careful of double quotes. Now what I did just now is I created a variable object and I stored a value in it. So we've looked at functions so far. They're kind of a way of doing something, but the objects are going to be a really important thing, variable objects. And so what I did was I created something, variable x, let's call it, and I can give it a value. So this is the standard way to do this in R, is to use this less than sign and a minus, which actually kind of creates a little arrow if you squint your eyes and imagine a little bit. So what I'm doing now is I'm storing a value in the variable x object name, and the value is 10. And actually, if you look up in your environment, you'll see all of the objects that have been created for you will be listed, and you can see variable x is just created, and it says it's numeric and it has the value 10. So if I ever type in variable x now, it's going to give me the value 10. I can treat this like any number. I can say variable x plus 4 and I'll get 14, because variable x is just storing the value 10. Now you could use equals to assign a value. Say variable y equals 8, and that will be fine. R has no problem with that. The reason that's sort of discouraged is it's a little bit misleading, because it looks like you're stating an equation, but what we're doing is we're taking the right hand side and assigning its value to the left hand side. So we're some expression, like for example, I could say variable z takes the value square root of 75 plus 8 to the power of 0.3, right? So this is we evaluate the expression, and then that gets stored into variable z, which comes out to be, you can see it up there, 10.5263, so forth. So the little assignment arrow is a little bit more like accurate about what's really going on there. It's not just we're saying this thing equals that and like solving some equation. And the equals is sort of we use the equals when we're setting the input parameters in a function equal to some values. So it's nice to not use the same symbol for different things, and so for that reason I'm going to be as consistent as I possibly can in using the assignment operator as like an arrow, which is literally, it's like less than minus, but we're going to think of this as a arrow going to the left. Now, okay, so you can use you can name variables in like these objects can be named. A lot of things are fine names. So what I've been doing is long name of a variable. I like to name them using what's called Camel Case, where you start with a lowercase word, and every new word you begin that new word with a capital letter. That's fine. This is not a good name because there are spaces. Spaces are no good. If you want to indicate spaces, you can put underscores. That's totally fine. You can use underscores for the variable names. Also, this is totally acceptable. You can put periods in to separate words. That's fine. You can actually names can have numbers too. You can have a number in the name. That's fine. You can, but you can't. Numbers cannot start object names. You can't have a number be the first character in the name of an object. That's not allowed. But it could be anywhere within. You can have a number in the middle of an object name. That's totally fine. So it's, and also so if I wanted to add 10 to that value, I would get 110. But if I put capital letters in, I'm going to, oops. Well, that defeats the purpose of that example. I wanted to show you that my example was going to be the capitalization. Actually, maybe you can see they're two different objects, right? Boys to men is with capital B and capital M has value 10, but boys to men with lowercase has value 100. So the capitalization makes a big difference. They're completely different object names as far as R is concerned. If I made a mistake and I want to get rid of one from memory, you use the remove function, and it's gone now. It's been, that object name has been completely removed from the memory of R. So the remove function is handy if you ever make a mistake. Now, so far these have all been single values. There's the objects that are a little bit more complicated, not complicated, but more elaborate, let's say, than just a single value, would be like a list of numbers, and those are called vectors in R. And if you are familiar with calculus and linear algebra and stuff, the word vector is used in the same kind of way. It's an ordered list of things. Now in R, What I said before is that you were given this little index of 1, and we saw that a whole bunch of times, right? The first item in the object boys to men is the number 100, but there's only one object anyway. In fact, it's actually a vector with only length 1. It's a list of length 1. R doesn't make any distinction. Everything's a vector if it, at the very least. There's no such thing as like a single number really. But it's just a vector of length 1. Anyway, if I want to create a list of things, I'm going to use the this combine function, the letter C. It's a super simply named function, but it allows me to take a whole bunch of things, 1, 5, 2, 4, 8. I'm separating them by commas, and what I get is a new object called vector1 that has 5 numbers in it. I'll type it in, vector1. Those are the 5 numbers listed. Now, the 1 on the left is giving you the index of the thing in the first thing listed on that line. So they're indexed starting with 1, 2, 3, 4, 5, and that's the last index. It's only listing the 1 for, that's the index of the number 1, which is the first thing listed on this line. To give you an example of something longer, we'll look at an example of something longer later. But anyhow, so what we have here is a vector object, and we can access individual numbers within that vector by just by using the same bracket notation. So if I want to get the second number from the vector, do vector1 bracket 2, and it'll give me the number 5. These are called elements of the vector. And so this is so if I wanted to, there's a lot of fun stuff we can do with vectors that makes a lot of math really easy. So vector addition, if I do vector1 plus 10, what it will do is it will add 10 to each number in that vector. So you'll take a look and see what we get. We're going to get 11, 15, 12, 14, 18. So R knows what I'm trying to do is add 10. It knows that 10 is just a number, and then this vector is a list of things. And I know it can't, what it does is it will just do that math to all of them. The same thing, vector1, if I do vector1 times 4, it's going to multiply everything in the vector times 4. And let's see, if I can do vector1 squared, it'll square everything in the vector. Now here's something at this point you should know in R on the console is if you want to go back to something that you just typed in and do it again or change it a little bit, you don't have to retype it. If you press up on the arrow keys, up will cycle through the previous commands, up. You can cycle through all the previous commands that you've done by pressing up, and then pressing down will go back. Down to the most recent, and then if you keep going down, it'll go to the whatever you're working on now. So let's see. So let's make another vector and show you. Let's vector 2. Let's have this vector be, let's see, 9, 6, -5, 10, and 0. Okay. So now if I wanted to do vector addition between two vectors, if I do vector 1 plus vector 2, what it's going to do now, because I'm doing a vector plus a vector, it's going to add them up index by index. So the 10 is, so notice what's vector 1 was that, vector 2 was that, oops, vector 2. And so when I'll do this again, this command. So you get 1 plus 9 is 10, right? 5 plus 6 is 11. 2 minus 5 is minus 3, and so forth. So that's what happens when you do multiplication, or when you do addition. If I was to do multiplication, vector 1 times vector 2, it knows I have two lists of the same length, and it's going to multiply them in pairs. So the 9 is the 1 times 9, then I have 5 times 6, and so forth. Same thing will be true for if I was doing division. Now, if you know about vector stuff in like linear algebra, and you wanted to do a dot product, you can do that in R, but there's another way of doing that. So when you do like multiplication like this, it's going to do pairwise products. Okay, so when you have a vector, one important function to know about is the length function. So if I do length, it's going to tell me how many things are in this vector object. The length of vector 1, it comes back as a 5. So vector 1 has 5 objects in it. Let's see. So length will tell you how long a vector is. Sum is another useful one. The sum function will add up everything in the vector and give you the sum, as you would imagine it would. Another one that is, let's see if I can. The difference function. That's a little funnier. What this is going to do is I would need to give it two vectors. Vector 2 comma vector 1, for example. Oops, I'm sorry. I'm sorry. I was thinking about something else. No. The difference function, diff, what it's going to do for the vector is it's going to tell you the difference between index 1 and index 2. So let's look at vector again. So 5 minus 1 is 4. 2 minus 5 is negative 3. 4 minus 2 is 2. 8 minus 4 is 4. So that's what the diff function does. You can see it's giving me it's resulting in 4 numbers because there's only 4 differences. Let's see. There are other functions that you can do with vectors, but let's see. We also want to understand some stuff about other kinds of data. So far, we've just been working with numbers. And so we can record a vector, well, I'll call it siblings, and I'm going to make a list. Mary, Terry, and Jerry are 3 siblings. So what I've created is another vector, but this isn't containing numbers, it's containing character strings, words. Right. So you can't do the same thing with character strings that you can. If I did sum of siblings, I don't know what it's going to say to me. It's probably going to say can't do it because you can't add up Mary plus Terry plus Jerry. That doesn't make any sense. So there's certain functions that won't work anymore, but you could still find out the length of siblings. And yes, there's 3 of them. Notice something though. I had to put quotes in double quotes. If I wanted double quotes to be in my in a character string, and I don't know if this is ever really going to pop up, but string with quotes. Let's say, how about Jerry? Let's say somebody's name is Jerry T-Bone McGill. T-Bone McGill. R will not like this at all. Hit enter and you'll see it's going to not know what's going on. The quotes are all over the place. I have to escape these with using a slash. This tells R that the character coming after has to be interpreted not as the end of my string, but as a character within the string. So that's the way to save double quotes inside a string. And if I now wanted to look at it, string with quotes, it'll, I'm sorry, I mistyped. String with quotes, mistyped. So you can see that's giving the whole thing. Now, it doesn't look good. If you want R to make it presentable, you have to use the cat function. Cat string with quotes. What that does is it kind of renders a string and all of the characters in it. And it doesn't give it using like that one as your index. It just renders it nicely. And so Jerry T-Bone McGill is how it would look if you wanted to like write it as text in some file or something. Now there's other so one thing that you may see often with your data is missing values. So sometimes we're recording data from some study, and maybe something is missing, or we couldn't make some measurement or whatever. R uses a special value called NA for missing data. So I'm going to make an object called missing data, and I'm going to give it the values 6, 7, NA, and 9. And that's fine. The letters, capital letters NA, are just interpreted as missing data. It's a weirdo. It's not a 0. And in some data sets, they'll put like -1 or -99999 for missing data. But R has a special animal that it uses for missing data. You can we'll talk a little bit later about how to kind of handle missing data and things we can do about it, but I want you to first here just be exposed to this idea. Let's see. So something else you might see is something that's not a number, something that it expects to be a number, but it isn't a number. I'll give you an example. If I say y is the square root of -5, and I know all of you are thinking, no, don't press enter. It's gonna. It doesn't like that because it said NaNs were produced. NaNs, not a number. So what is the value y? Y is not a number. NaN, not a number. It doesn't handle complex numbers, and so it doesn't like that square root of -5. So if you ever see NaN, that means some mathematical computation was done that produced some invalid number. Okay, so we've looked at number data and string data. Another one that's important is true and false, like logical data. So you can so the values, it's true and false are the two values. They're capital. If you do just capital T or capital F, those would be the same. R interprets capital T and capital F as true and false, unless you go ahead and assign some other value to the capital T object, in which case the capital T will not be true anymore. It'll be whatever that is. But if you ever do that, if you want to use the capital T as shorthand, you can remove it from being redefined, and then you can then you can use that as shorthand. So so let's make an answers object. Let's 2GFFT, and so my answers object is the 5 values: true, true, false, false, true. And so this comes in if I say 5 less than 8, is 5 less than 8? True. That's the kind of place where you would see true coming out. And 8 equals, so here's 8 equals 9. If I say 8 equals 9, it doesn't, it's 8 equals 9. This is the double equals, is the conditional equality. It's testing equality. No, false. 8 does not equal 9. We'll talk a little bit about conditionals later on, but I wanted to show you kind of this true and false. That's the way the data is held in R. All right, so we're now going to learn about sequences in R. A sequence is a way of creating like a numerical pattern and doing it kind of quickly. The simplest notation you can use is the colon notation. So if you type in 1:10, that's going to be interpreted as the sequence of numbers from 1 up to 10. So you can hit enter and you'll see that this immediately gets interpreted, like evaluated, and the result of it is 1 through 10. You can do it in reverse, 10:1, and it'll do the reverse sequence. So if I did 89:115, it would do those numbers. No, you notice here, this is the first time we've seen the output takes more than one row, and you can see that you have the one index for the number 89, and then it goes across, and just so you don't have to count, it tells you that 18 is the index of the next number, 106. So that's why the row starts with 1 and then 18. So it'll tell you the index of the first thing in that row. That can be pretty helpful. There's a function for vectors called reverse. So if you do a reverse, REV, it will reverse a vector. So if I reverse the vector 1 through 10, that's going to give me the numbers 10 through 1. If you mess around a lot, you can I mean, if you reverse the reverse, you'll just get back to 1 through 10. So reverse reverses the order. The rev function reverses the order of a vector. Now if you wanted to make a sequence where you're skipping by numbers, you can use the seq function. So if I do seq 1,9, that's going to be a sequence from going from 1 up to 9, and it'll be, by default, it'll count by ones. So that's the same as doing 1:9. But if I wanted to count by twos, 1,9, I can actually, let's be more explicit. I say by equals 2, and it's going to now start at 1 and then count by twos. 1, 3, 5, 7, 9. So it's counting, it's doing every other number. And you can also specify how many numbers you want in a sequence. So if I want to have a sequence going from 1 to 20, and I want to have exactly 7 numbers in my sequence, and I want the first one to be 1 and the last one to be 20, I want to say length equals 7. And it's going to space them out, exactly spaced out as much as it needs to for there to be 7 numbers. Oops. I'm sorry, I put the colon in there. 1,20. Here's what I was looking for. So you can see it starting at 1 and then 4.16, that's 4 1/6. Then you have 7 1/3, 10 1/2, and then going up. So there's the difference between them is exactly the same. In fact, if I wanted to use the diff function on this vector, all the differences should be the exact same. Yep, there's exactly 3 1/6 between each number in the sequence. So let's see. In addition to sequences, you can use the rep function to repeat numbers. So it's repeating you repeat the first number and how many times you want to repeat it. So at rep 2 comma 4 is going to take 2 and repeat it 4 times. So 2 2 2 2. You can repeat. Now you can make things interesting by repeating, say, a sequence. I can repeat the sequence 1 to 3, so 1 2 3. Let's say I want to repeat it 5 times. So it's going to do 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3. It's like it's doing a waltz. So you can combine the rep function with a sequence function. Whatever, when you do rep, the first thing you put in here, like I could have the word hello repeated 7 times if I wanted to, right? Anything you put there, it's going to repeat. Whatever object is there. If the object was a single word, if it was a vector, it would repeat that thing that many times. So let's play with some stuff about vectors, like the indexing of vectors and that kind of thing. So I'm going to create a vector, a bunch of prices of things that have been sold on eBay. I'm going to just make these numbers are not really going to be too meaningful to us, but I'm going to put them in 94.7, 99.2, 9.4, 101.6. So these are just some kind of bogus numbers, but I want to just talk a little bit about what you do with the indexing of things. So as we already know, if I wanted to look at the first number in my vector, the first index, I use this bracket notation. This is going to be the first index, right? 88.8, and that's exactly what I have in the first index. Let's say I wanted to look at the last entry in the vector, but I wasn't exactly sure. As you know, the length of a vector, that tells you how many indices there are. So I could go to eBay, index length eBay. This is going to give me the last entry. You see? So I don't have to explicitly know what the last index is. If I tell it to go to the index that's the length of the vector, that is the last one. And I could even look at this is the penultimate. That's the one second from last. That I'm doing length of eBay minus 1, which would be the 8th entry, right? So you can index things like that, and you can also specify which indices you want using a sequence. So I can do eBay then 1 through 4. That's going to give me the first 4 indices, 1, 2, 3, and 4. Check that out. So this is where sequences really come in handy when you want to get specific entries from your vector. You can also specify exactly what you want using a vector of indices. So if I want the first, the 5th, and the 8th entries, I can specify those using the C notation. C creates a vector, combines 1, 5, and 8. So I'm going to get the 1st, the 5th, and the 8th entry from my vector. Negative indices are a way of excluding certain entries. So if I want everything except for the 5th one, I do eBay minus 5. What that's going to do is it's going to just exclude the 5th. So I'll get everything except for the 5th. So the 5th one's excluded. It's the 1st, 2nd, 3rd, 4th, then the 6th, 7th, 8th, and then 9th. You can exclude an entire chunk, but if you did minus 1:4, that isn't going to work because it's going to start from -1 and go up to 4. So you need to put parentheses around your sequence, so it'll create the sequence and then it'll make them all negative. That will get rid of the first 4, and you'll have the 5th through 9th. That's the same as if you did 5:9. That's 5th through 9th. You can see that I'm getting the exact same results. But sometimes you don't know which ones you want, you just know which ones you don't want. Now, another thing is you can, if I have a vector, let's have a very simple vector. This is the vector that has 1, 2, 3. Okay, you can specify names for the entries of your vector. So you can say the names of my vector x are going to be, let's say A, B, C. So now I can, if I look at what is my x, it's each of these entries is indexed with a letter as well. So if I wanted to, if I maybe that, this might be handy in some cases, but if I want to get the B entry from my vector, I can specify x, and then the index, instead of number 2, I can say letter B with double quotes, and it'll give me that entry from the vector. Now, just taking a quick look at my eBay vector, right? So these are the numbers. Let's suppose that I made a typo when I entered this, and the 7th one was supposed to be 89.2 instead of 99.2. You can replace just a single value by specifying it like this. I can say eBay 7 and replace it with the number 89.2. And now everything's the same except for that 7th entry. So you can modify values in the vectors individually by indexing them like that. Now, another way of getting specific entries from a vector is with a vector of logical values. Now this may seem really weird. So if I do eBay, I'll do another little dummy vector x, and I'll have the numbers 6, 3, 5, 2, 3, and 4. Okay, and let's say I want to get specific values. Sorry, I want to do x, and I want to get the values. I'm going to say, let's say T, T, F, F, T, T. What this is going to do is it's going to give me the 1st, the 2nd, but not the 3rd, not the 4th, and yes to the 5th, yes to the 6th. Now, this by itself doesn't make a lot of sense to do. But the thing is, if I was to take my vector and say, is my vector greater than 3, what it's going to do, it compares each of the entries of the vector one by one to the number 3, and it returns a vector of true and falses. So what I can do is I can combine those two ideas in order to get a subset of a vector based on a condition. I can do x where x greater than 3. What that's going to do, it's going to only return it's like a subvector or sublist of things in that were greater than 3. So those were the entries in the x vector that were greater than 3, 6, 5, and 4. So I don't have to know what indices they were. I can just say this is the condition that I want. I want all the numbers that are greater than 3. You can, if I want to know the numbers of those vectors, I can say which is a way of getting the indices. So you can see which indices. So let's take a look at this vector. It says when I say which, where x is greater than 3, well, that is the 6. That's the first index, the third index, and then the 6th index. So the which function tells you which indices, which elements of a vector satisfy this condition. So if I specify explicitly like this, I should get the same exact thing, because this is just saying I want to get entries 1, 3, and 6. So this, but you don't have to. You can use the which notation if it is useful, but most of the time we probably can just take the shortcut and just put the condition. So we want to spend a little bit of time looking at different conditionals. The basic operators are greater than, less than, and equals, but then you have greater than or equal to. So let's take a look at some. Is 9 greater than 7? True. What about is 9 greater than 10? False. Is 9 greater than or equal to 9? It's true. That's greater than or equal to. You can do 7 less than 10. True. You can do 7 equals 10. False. 7 is not equal to 10, but is 7 equal to 7? True. 7 is equal to 7. So you have to use a double equals. Now I try to put spaces between my operators and the objects they're operating on. It's good practice. I was a little sloppy. I missed the spaces, but it's not going to affect things in R. R doesn't care. Also, if you put the exclamation mark, it negates the operation. So if I said is 9, or let's say is 9 not equal to 10? True. It's true. 9 is not equal to 10. You can also negate a logical expression. The opposite of true is false. So I can do this. What's the opposite of 9? Is 9 equal to 10? Well, it's false, but then the opposite of that is going to be true. Okay, so that's what the exclamation mark does. It makes any logical expression the opposite. So it's equivalent to the word not. You can also combine logical expressions. So I want to say, like, say, is 7 greater than 2? And is 9 less than 10? True. What about is 7 equal to 2 and is 9 less than 10? False. The and requires that both things be true for the whole statement to be true. That's the way and works. So the ampersand is the logical and. That's the way you conjoin different conditions. With an and, they both have to be true. But you can also ask if you can specify this or that to be true. So you can say 7 equals 2, or actually I'm using the pipe, so it's like the shift slash 9 less than 10. So this is going to be true because it only requires one of those two statements to be true for the entire thing to be true. It is the case that 7 is not equal to 2. So you have false on one side, but then you have true. So if one thing's false but the other is true, one or the other, that is satisfied, right? That's all you need, is one of the two things to be true. By using and or, and by grouping things in parentheses, you can build really elaborate conditions. And these are ways that you can extract rows from your vector, or entries from your vector, or as you'll see later, you'll be able to extract rows from what's called a data frame based on certain conditions, and that's going to be really handy. Let's see. The in operator checks whether some vector is in another vector, or whether the elements of one vector are in another vector. So let me show you an example. I'm going to create a vector 6, 3, 5, 2, 3, 4, and let's say I want to get all the values that are either 2s or 4s. So I want to get, if I check x, I do percent in percent. So I want to get all of the elements. This is what this is going to do. It's going to give me all of the indices of this vector, as long as that certain number is in this other list, 2 and 4. Basically anything that's 2 or a 4. So what this tells me is that the only elements the only indices that represent a number that's either a 2 or a 4 is the fourth, which is, as you can see, the number 2, and then the sixth one, which is the number 4. So that's what the in notation. It's a way of checking whether values are whether basically they're any of this other. So it's kind of a way of finding the overlap between two vectors. So what values are common to both? So if I wanted to get just those, I can specify that as the index. I want to get all the x values indexed by this condition, x in 2, 4. And what that's going to give me is those two numbers, because those are the fourth number and the sixth number. If x was, let's make x a little bigger, 3, 5, 7, 2, 2, 4, 6. Okay, and I'm going to repeat this. What I'm going to get is 2. So it went through and it checked and said, yep, I want that one, I want that one, and I want that one, and that one. And it didn't get any of the others. So that's why it gives me 2, 4, 2, 2, 4. Because those are all of the values in order that are common to the vector 2, 4. It doesn't matter that the order is different in like if I had done 4, 2, it would give me the same exact thing. The order of this doesn't matter. It just it's giving me the same order as the original vector x that they were found in. So this is going to be handy for finding values that are common to two vectors. Let's see some other stuff. Checking whether values in a vector are NAs. We talked a little bit about NAs, so I'm going to create a vector that has some missing values. Let's actually have it be true, true, false, true, NA, true, true, false. So let's say I was recording an experiment, and when it was a failure, I would record a true. When it was a failure, I would say true. If it wasn't a failure, I would say false. And if I didn't record the data, NA. And so if I wanted to get all the NAs, you don't use the double equal sign. It's going to give you weird results. What I want is to use the function is.na. Is.na is going to give me a true for all of the values in there that are NAs. So if I wanted to, let's see, if I wanted to just get all of the values that aren't NAs, there's a couple ways we can do that. Actually, we'll handle missing data later. But so this is just to illustrate again that NAs not available are a kind of a different beast than other stuff. You can't treat it like a number. Like it's not going to satisfy the condition double equals. It doesn't work like that. Let's see. So we'll mention one thing. There are certain functions, and we haven't really learned about this, but actually, you know what? I won't even mention that. We'll talk about mean later. Okay, we've really covered the basics of vectors. I want to move on to matrices. So let's make a new vector that's the numbers 1 through 12. But I want to arrange this vector not in a row, but in a grid. I want to have 4 columns and 3 rows. So if I use a dim function to give this thing dimensions, and I'm going to give the dimensions of 3 rows and 4 columns, so 3, 4. What that's going to do, if I look at my x vector now, you realize it's not a vector at all anymore. It is a something else. It's a matrix. And it is the entries in this object, this x object now, are now indexed by a row and a column. So notice the way these rows are labeled is 1 comma, 2 comma, 3 comma. So if I wanted to get the first row, I would do x1 comma, and I don't specify anything after the comma, and it's going to give me the whole row. Likewise, if I wanted to get the first column, I do comma 1, and that's going to give me that. Of course, it's giving to me across, but that's it. The column is a vector when you remove the other dimensions, right? If I want to specify just a specific value, I can look at entry 3 comma 2, that's the third row in the second column, and I can get that number 6. So this has 2 dimensions, and a matrix could have more than 2 dimensions. It could have, there are 3 and 4 and 5 dimensional and whatever dimensional matrices you could build. But matrices, looking at a 2-dimensional matrix is really useful because it'll get us used to this kind of format, which is similar to data frames, which we'll be spending most of the time working in data frames. Just a couple things about a matrix. Once you have a matrix, you can label its rows. So I'm going to label the rows with this letters vector 1 through 3. Letters is a fast way of getting the letters A, B, C, D. Letters is the vector A through Z. I think letters lowercase is going to be the lowercase letters. So if you ever need to quickly just get the first, say, if I want to get the first 5 letters, 1 through 5, A, B, C, D, E, that's a good way to get it. So letters is a built-in vector in R, in base R. Anyway, so call names of X, this is the column names, I'm going to label it with the numbers 1 through 4. And now when I look at X, the columns are indexed 1 through 4, and the rows are indexed with the letters. So if I let's see if I would do this, if I wanted to look at, I can look at, B, comma 4, and I should get my 11. Yeah. So it may be handy to do it to label rows and columns. And one function that you can do to matrices that can be useful is a transpose of a matrix. And it's just, the function is just the lowercase letter t. And what it's going to do, it's going to flip it on the diagonal, so rows become columns and columns become rows. You see that? You can, when I created, well, we'll deal with matrices a little bit more later, but I guess that's pretty much all I want to say about matrices. And I think when I say before that you could have a 3 or 4 dimensional matrix, it's actually not called a matrix anymore. It's called an array when it's higher dimension. But anyway, so far all of these things have had just one type of data in them. So we've had vectors that were numerical, vectors that have letters in them. Now if you wanted to combine different types of objects together, there's R has an object type called a list. And so I'm going to we have this matrix X. I'm going to create a list, and I'm going to use the list function to create it. I'm going to have the numbers 5, the number 6. I'm going to have the value true, the name George, and I'm going to have my X matrix. All of these things one by one, and they're going to be my list. Now let's look at what my list looks like. So my list is indexed in a weird way. You can see these double brackets. Double bracket 1 gives you the first thing in the list, which is the number 5. Double bracket 2 is the second thing in the list, which is the number 6. Double bracket 3 gives you the word true, double bracket 4, so forth. So double bracket 5 gives you that matrix X. So if I wanted to do my list, if I wanted to get the matrix out of that, I would do my list double bracket 5. And if I wanted to look specifically at entry, let's say A3, I would have to index it like that. I first put the double bracket 5, and then I put my regular index A, 3, which also could be indexed as 1, 3. Same thing, but that'll get me that 7. Lists are going to, they can sometimes be handy. If you have, and actually it's good to know about lists because there are certain functions that it will, when the function gets run, it will have a lot of output of different types of things, and they will be returned in a list. And so this is good because then you'll know how to get those things out of that list. Let's see. Okay, we're going to finish things off with a discussion of, we're going to talk a little bit about data frames. So data frames is the most sophisticated kind of data object that we'll be dealing with, and then actually after that we'll talk a little bit about working with files. So I'm going to create some data, and I want to put it all together in one kind of thing. So first of all, let's suppose I have recorded the colors of a bunch of slugs. Red, the first one was red, the second one was brown, the third one was red, the fourth one was red, and the fifth one was white. These are exotic slugs. The lengths of these slugs were recorded, and the lengths were 5, 4, 6, 5, 3. Let's say centimeters. Okay, so I've got two vectors. I want to combine them both in one data object called a data frame, which is where I'm keeping all my data related to these slugs. So I'm going to create an object called slugs and use the data.frame function, and I'm going to combine colors, lengths in that order. And what it's going to do is create something. I'll show it to you. We've got colors and lengths as the two columns in this thing, and we've got them indexed 1 through 5, and you can see the first one was red and had a length of 5, the next one's brown with a length of 4, red with a length of 6, and so forth. So what I've done is I've created this thing, this data frame called slugs, and it has all this information. Now if I wanted to access the lengths of the slugs in this data frame, I have to use this $ notation to access the different variables or columns that are in it. So this is a way of just getting the slug colors, slugs $lengths, and I can retrieve those back again. If I wanted to create a new column, I can use $ and create a new variable name, weights, and I can create, let's say the weights of these slugs were these numbers, and now I've added another. So let's look at what it looks like this now. You've got a third column that's been added on. And just as with matrices, you can access individual entries using row column notation. I can get everything about the third row. I can get everything about the first column, but I can also access a column by its variable name. So I can get the fourth row, and I can get the length. So this will give me the length of the fourth slug. But it has to be row column. It's always row column. So now it's going to be handy to remember that the you can get the rows based on certain conditions. So let's suppose I wanted to get all of the red slugs, information on the red slugs. Slugs colors equals red. This condition will give me falses and trues based on whether the slug was red or not. And so I use this condition to give me the rows. So I do slugs bracket slugs $ colors equals red, comma, and I want to get all the columns. So now I get my subset of data for just the red slugs. This is how I can specify certain rows. You can also, let's suppose I wanted to get, and I want slugs lengths, let's say less than or equal to 5. So I want to get all those slugs that were red and less than or equal to 5 centimeters. I combine those two conditions using the ampersand, and I hit enter, and it's going to give me just those rows that satisfy that condition. So this is what we were building all of those skills for. It's going to be really useful to look at the to extract subsets of data, to use conditions, and to use less than, greater than, equals. Notice how I had to specify the slugs $ colors. In order to access that variable within the data frame, you need to do that, unless you use this function called attach. Now this sometimes will cause problems because I have variables that are called colors. It doesn't like that because these variables match variable names in the data frame, so it doesn't like that. But what attach will do, let's remove detach, remove, unattaches it. Now I'm going to remove colors and remove lengths. So now if I do attach slugs, if I wanted now, as long as the slugs data frame is attached, I can reference the variables in there just by the variable name. I don't have to say slugs $. So now I could go and do this, and I can specify slugs where colors equals red and lengths is less than or equal to 5. That will work now because I've attached the data frame. Once I detach slugs data frame, doing this will not work. It's going to give me problems because it doesn't know that the variable I want is in this data frame. I have to explicitly state that, or I have to attach the data frame. So there's a couple other useful things with data frames. Now this isn't going to be much, but if you have a large data frame, the head function will give you, well, you know what I'm going to do? I'm going to let's see, let's find great. There's a data frame that's already built into R called cars. It has the speed and distance of a bunch of car numbers. So I don't know exactly what it is, but there's 50 things in it. Look how it takes more than a page to display it all. But if I just wanted to look at the top few entries, the head function is useful. It's going to show me just the top 6, the first 6. In fact, you can actually specify how many you want. I can look at the first 3, and you can also look at the tail to look at the last 6, or you can change that to be the last 4, for example. The head and the tail function are handy for looking at if you want to get a quick glance at a data frame that's very large, if you just want to see what the data looks like a little bit. Another one that's useful is the summary. The summary function will give you numerical summary. Now it'll also tell you if I did, so here this it tells me my speed and distance, and it gives me the minimum and some statistics, the mean, the median, and some other stuff that we haven't really covered yet. If I look at the summary of my slugs, the first variable, colors, is oops, I'm sorry. The first variable is categorical, and so it's telling me there was 1 brown, 3 red, and 1 white. But for the others, since they're numerical, it'll give me the numerical summaries. And you can also look at the structure by using str. It'll tell you this is a data frame. There's 5 observations of 3 variables. So there's like some summary information right there. And it tells you the variables. The first one is colors, and it's a categorical factor because it's qualitative information. There's 3 levels. Levels are different values it can take: brown, red, and something else. It's not going to tell me everything here. The lengths, it says it's numerical, and the values that occur, 5, 4, 6, 5, 3. When there's only a few values, it'll actually list everything. But if there's more, it's not going to list them all. But the str is a great function for looking at the structure of a data frame. Now, as you know, if you want to find how long a vector is, you use length. But if I use length on my data frame, it will not give me the right answer. It's giving me 3. But that's I think it's telling me there's 3 variables. What I want is n row, the number of rows of slugs. I'm usually interested in how many rows there are. So length of the cars data frame 2, but that's 2 variables. It's n row. There's 50 rows. So if I have a vector, I can use length, but for data frames, you typically are going to be wanting how many rows there are, and that's something you check with n row. Let's see. I guess the other thing that's worth knowing is, for data frames, let's add another. Let's say I have the pH that was measured for each of these slugs. I'm going to create 5.6, 6.5, 3.2, 5.6, 6.3, 5.5. I'm making these numbers up. I don't know what's realistic. But let's say I want to add that to the data frame. You can use a function called cbind. Cbind, you can take a data frame and another data frame or a vector like pH, and it squishes them together. So oops. Oh, you know what? That's the reason why. Because I'm jumping ahead. I wanted to add another row. If I want to add another row to it, I have to use rbind. Let's add another row to slugs, and the row is going to be another red slug of length 2 and a 15.6. Rbind adds another row. Okay, so you can see it's added that to the bottom of it, but that didn't save my data frame. My slugs data frame only has the 5 rows. In order for me to save that, I have to take the result of this, and I have to assign this to the slugs object. Now slugs has 6 rows. Okay, what I was going to do before she'll work now, if I wanted to tack on an additional column of pH, I can use cbind, column bind. So it's going to bind a new column onto the right. This is what it's going to look like. It's going to have my columns, and then it's going to add the pH column. But again, if I want to save that, I have to assign that to my data frame. So the result of the cbind function has to be saved somewhere, and it's going to overwrite my slugs. So now slugs is a larger data frame. You can check whether objects are of different types, and this is there's this is function. So is dot vector checks whether an object is a vector. Is.data.frame checks whether an object is a data frame. Is.numeric will check whether something is numeric. So is.numeric slugs, let's say lengths. Is lengths a numeric vector? No, it's not a number. Is it a vector? True. Oh, because I did rbind, now it thinks r is that length is a word. So the rbind is a dangerous one to use because it might change the type of data. I think I want to change my lengths. Slugs lengths. I'm going to do as numeric. As makes it become numeric. So now, if I check is, what is the slug lengths now are now values instead of strings. And the same thing actually needs to be fixed for the weights. I'm going to change the weights to be numeric because they got converted to strings. Let's just make sure my data frame is good. I'm going to look at its structure. Yeah, so the colors are a factor, but the lengths, weights, and pH are all numeric. So this is what I was expecting to see when I was asking, is slug length numeric? Yes, it is numeric. Is dot character slugs $ colors? Yes. Oh, colors. They're not. It's not character. These are factor. Factors are a little different than characters because what factors are, they're categories that encodes as numbers. So like it's so the value brown is encoded as, I guess, a 2. Is that the case? Let's see. I guess that you have red is a 2, brown is a 1, red is a 2, and white's probably 3. So you could see up above when it said colors was a factor with 3 levels: brown, red, so forth. It's encoded it's saved as 2, 1, 2, 3, 2. But if I wanted to save them as characters, I can say slugs colors as dot character slugs colors. Now, if I look at this structure, I've changed my colors to be characters, like character strings. It actually can be useful to keep them as factors, but sometimes it's more natural to have them as character strings. But we'll see why. I mean, one of the reasons why is that when you have them as characters, you can add a new value that isn't already in there. But if it's a factor, you need to somehow you have to make sure that R is ready to bring in the new factor level. We'll get into all of this stuff more later. I don't want to get too bogged down on this detail stuff. Let's see. Okay, we've talked about removing. If I there's another way to remove. You can use the remove. You can also use RM. Let's say I want to get rid of slugs altogether. RM slugs. RM is going to remove the slugs. So slugs is gone. RM or remove, both of those will do the same thing. Now let's see, for files now, if I want to bring in data, the first thing you probably want to do is figure out what working directory you're using. The working directory is the location on your computer where you're going to be saving files and opening files from. And in Rstudio, you go up to session, and you can set the working directory and choose the directory. This is probably the easiest way to do it. Now in a Mac it's a little different, I think, but here you can actually go and you can I'm going to go to my I'm going to go where I have my ABS 350 data. Oops, that's the data sets. This is, no, it's the data. That's what I want. Here, this is what I want. I want to open this directory. So what I've done is I've set the working directory to this folder. And now I can open, if you go over to the right panel under files, it'll see a list of all of the files that are in your working directory. And so if I wanted to open, so here we have a file called plant height. I want to open that up. It's a CSV file, which is a comma separated variable file. So if I want to open that up, let's plants, I'll say read.csv is the function I want, read.csv, and I just can type in the name, plant height.csv. Now what I've done is I've taken the data in that file and it's now been put into a data frame called plants. Oops, I titled it wrong. Let's spell it correctly. Plants with an N. Okay, let's look at the data frame. Whoa, it's big. Okay, so it's big. I'm gonna look at the structure. So we have factors, plant medium, the water frequency, and the height. Okay. Then if you don't know exactly where the file is on your computer, what I often will do is, if you do, let's say, tree data read.csv, instead of typing in the file name, you can do file.choose and then another parentheses. This function file.choose will allow you to go around and navigate through the computer to find what you want. And let's say I find it here, and it's, oh, my trees data is right there. So click open, and then you open it like you would anything else. So file.choose is a great little function that allows you to search for the file like the way you are normally used to doing so. There are other types of data. If you have table data, which would be like a text file where the data is separated by tabs usually, you would use read.table. And depending on the data you have, we'll mostly be using CSV files. Now, that's how you open a file. If you wanted to save, you actually use the write. So read and write are the kind of corresponding functions. So if I wanted to say let's say my tree data, write.csv, and let's say I want to have the tree data saved, and I would giving it a new name called new tree data.csv. Like, this is what this is going to do. It's going to CSV, you have to be careful to spell it right. So write.csv, and then it'll save a CSV. Now I think I might not see it here. I might need to refresh. Okay, so what I wanted to do is click this refresh button at the corner, and then I'm going to go down and see if indeed, I wonder if these are, oh, here it is. It's sorted by modified date. If I was sorted by name, yeah, it's in here. New tree data is now saved. If you want to save a so CSV is handy because it can be opened by people who aren't using R, but the most kind of space efficient file format is an R data file. So if I wanted to save an R data, I can use the save function, save tree data, and I would call file equals, let's say, trees.rdata. R data is that's a data file type that's specific to R, and it's really an efficient way of storing the data in a compact way. So now if I look through, we'll see that the most recent file is trees.rdata. Okay, so if you want to load an R data file, you just type load and then file equals trees.rdata, and the object that it gets saved as is going to be the same as the name. It's going to be trees. Yeah. For load, if you wanted to save it as a different, let's see. I think that once you do that, you can, if I wanted to change the name of the object, I can save that as a different. So new tree data, I can copy that data frame to a new data frame with whatever name that I want. That's the way you would do it. I think this is pretty much everything I want to say. I guess the last thing is, when you're done working in R, Rstudio is going to save an image of your environment, which is like everything you've been working on, and all of the files that you've things that are in memory. If you type save.image, and then you type a name, file equals August 14th.r data, what it's going to do, it's going to save an R data file that has everything that you're working on, everything that's in the memory, into a data file called August 14th, which you could then open up next time you're in R. So if you don't want to save every single one of your objects and data frames individually, you can just save the image of what R is working on, and then open it up at a later time. Now, I happen to have some massive data files in my working memory right now, which means it's still saving. It's taking a while, but that shouldn't be the case for you. Okay, so that's it for kind of intro to R and working in R. And we're going to be going into more data, learning more about specific kinds of data, not just in R, next.